Hello, in this video we're going to see if the formula is correct in Veritasium's video on a 100 prisoner riddle. And this is part 2. I had a part 1, we went through some ways to calculate the different loop sizes. And here I'm going to refer you to Veritasium's video. It's a must watch, the riddle that seems impossible and even if you know the answer. It's an amazing video, and actually the solution to it have just intrigued me so much. Now in the video, at 9:24 in the video, he flashes a formula that supposedly is used to calculate these probabilities, or at least the number of ways the various loops can happen. And here it is. And I went through 2 or 3 different ways to calculate the probabilities, and I could not match sort of what this formula is doing. And it just dawned on me tonight after work what this is even saying. So in short, my guess was wrong. So I was wrong. The formula is correct. And now let's understand it. So that's the goal of this video, is to understand this formula that Derek flashed in his video. Also a must watch is part 1 of this video, because we're going to use a lot of the nomenclature and techniques that we use from part 1, and it would make this video way too long if I had to reintroduce them again. Okay, so an example from part 1 is we calculated for n equals 9 all the possible maximum loop sizes. And one of those was k equals 3. And all the possible loop sizes were here. And so this represents 3 boxes are in a loop, another 3 in a loop, and another 3 in a loop. So that's 9 total boxes. And there's, 3 groups of 3. This here says that there's, 3 boxes in a loop of 3, 3 boxes in a loop of 3, 2 boxes in a loop of 2, and a loop of 1, and etc. And these are all the possible combinations where the maximum loop size is 3. Now, what this formula is doing up here is, well, first of all, let's look at these and look at the number of 3s that repeat. There's 3 of them here. There's 2, there's 2, 1, 1, 1, 1. That's what this first part is doing. It's calculating how many repeats of that k, or in our case 3. So how many repeats are there? There's 3, then 2, then 1. And then it's actually, so cycle through how many k's in each order. So in our case there's 1 to 3 in this example. Now if you watched part 1, it's actually so easy to calculate the probabilities associated with the 3s, right? So once we calculate the probabilities with the 3s, we reduce them. So for example, if we get rid of the 3s, then there's 3 boxes left over. And so we can then we can look at how many ways of 3 boxes can we have a maximum of 2, or how many different ways can we have a maximum loop size of 1. That's what this piece is doing. It's recalculating those smaller loops. So in loop, when j equals 1, or there's just 1 repeat, right? So that probability is easy to calculate. Then we get rid of it and we're left with 6 boxes left. So then we look at all the possible ways that we can have orderings of a maximum of loop of 2 with 6 boxes, and those are the 3 cases. And then we go down to 6 boxes, maximum loop size is 1. How many ways? And again, that's what this is calculating. And we'll go through this specific example on the back page. So basically what it's doing is it's reducing the number of orderings. So it takes out the 3s and calculates on a smaller order. So it's a recursive problem. And the R program that I created for this is quite fast, surprisingly fast. I don't know if I'll be able to do all the K's in 100 because there's just so many, but I'll share the program in the next video. So this one, so let's go through that again. So let's assume there's assume K repeats J times, all right? And you must watch part 1 to understand how we're calculating these probabilities. So this is the formula, J equals 1 to K. And so at some, we're just going to assume that we're at the Jth level. So K repeats J times. So we take, of the n boxes, we're picking K of them. Then there's K minus 1 ways to jumble those boxes up once we've picked them. Now those K boxes are gone, and there's n minus K boxes left, and we want to pick K of them. And then we jumble those up, K minus 1 different ways, factorial different ways. And then we keep going until we get to the Jth repeat, which means there's n minus J minus 1 times K boxes left. We pick K of them, and then we mix those up, K minus 1 factorial different ways, but we've overcounted. So since the K repeats J times, we've overcounted by 1 over J factorial. And this will make perfect sense when you watch part 1. Now, I ran out of room, so the formula continues down here. But then you reduce the problem. Remember, there's J repeats of K, so that means there's n minus jk boxes left. And then we want to find all the loops where the maximum was 1, and then the maximum was 2, and then we keep going until there's question mark. And then that's what that constraint at the top of the formula means. So this piece here, when you do the math, reduces to this piece right here, all of this. And then these sums of the smaller, loops or orderings is what this is, right? Now my notation's a little different. I have the n out front and then K, but I think in his notation, the T is first and then the N is second, but it's really the same thing. My mind works better like this, so that's why I have it. So let's go through an example using this formula, and then we'll call her quits. So let's find L93. So that's 9 boxes, and K equals 3. Okay, so the maximum loop size is 1. Okay, so see part 1, and we calculated this a different way in part 1, and it comes up with the same answer, which is not surprising, I guess. So n divided by K is 9 divided by 3, which is 3. So 1, 2, and 3 repeats for the number 3. So let's set J equals 1, and notice here that these are all the possible combinations where we have a 1, 3 in the beginning, and then the formula says n factorial, j factorial, k to the j, n minus jk. So that's 1 times k, which is 3, which is 6 factorial. Then we reduce it. We go from, we reduce it n minus jk, so that's 6. And then we go from 1 to the minimum, which is 2. So L61 plus L62. So when we calculate these, then we add these, multiply it all together, and then that's that iteration. Now we go to J equals 2. We get 9 factorial, J factorial, K to the J, and then no, this is J, and so this is this piece, n minus jk. J is 2, k is 3, so that's 6. N minus 6 is 3 factorial. Then we go down to 3. We've taken away 6 boxes, so there's only 3 left. And then we cycle from 1 to 2, and then we're done. Now it's this case, and this is actually why I did this example, is now J equals 3, the minimum, according to this formula, is 0. okay? But, so we go from 1 to 0. Now, some programs would just, hey, that means you do one iteration and you stop. But in R, it goes from 1 to 0, you know. All right, so this piece out front is this here, and then it reduces to 0 here, right? N minus 3 times k, which is 3, so it's 9 minus 9, which is 0. And then we go from 1 to 0. Now, you have to have a condition. See, this is 0, and this is counted as 1. In your recursive formula, you have to have base cases, right? And this is one of those base cases where it's a 1, because you have to have this calculation in it, and that's a 0. And these are the, you know, this is the possibilities for loops of size 3 with a repeat of 3. Well, anyway, so that's the basic understanding of the formula. The next program will be an R program. Now I've created several little programs. Some are not very powerful as far as meaning big ends, but they're powerful on illustrating what's going on. So I'm going to include those just because I think it's informative. But then this recursive formula that Derek provides is really the workhorse or the star of the show. Next video will be an R program for these calculations. So I hope you enjoyed this, and I'm so glad that I didn't officially make a bet, because then Derek would be 2 for 2 on bets. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.